Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss rotation of coordinate axis or properties of vector under rotation. Let's begin. Properties of vector under rotation, that indicates what are the changes occur when a vector is rotated with the reference to that of coordinate axis. Let us discuss the manner in which a vector transforms under rotation. Let us consider the three-dimensional Cartesian coordinate system x, y, z. Let the rotation be around z axis, the origin O, and the rotation be around z axis, that is x, y coordinates are rotated counterclockwise. Clockwise means the directions like this, and when counterclockwise, that indicates the opposite to that of direction of clockwise, that is anti-clockwise. The direction is just opposite the direction of that of clockwise. This direction indicates anti-clockwise. For say, let rotation be around z axis, that is x and y coordinates or x and y ordinates are rotated counterclockwise through angle theta, keeping the position r vector fixed. Let the position vector be r vector, which is fixed, rotated to an angle theta, where P be the point with the coordinates x, y, z, such that r vector is equal to x I cap plus y j cap plus k z cap. K z cap is the position vector. Similarly, let x dash, y dash and z dash be the coordinates of the point when the axis is rotated by an angle theta in the new coordinate system. See the figure. If we rotate that of ordinates through that of z axis at an angle theta, then the position of that point P of x, y, z is changed to that of coordinates x dash, y dash and z dash. See the figure. If we rotate x changed to this is x dash, y dash. Now, for our mathematical consideration, let us draw the point BC and perpendicular from C to that of X, that is A, this is perpendicular the point is B, D, and the angle B theta as it is rotated along Z axis, or we keep Z axis as constant and rotated in direction of X and Y. So similarly for that of Y section, draw the perpendicular from this point, let it be H, be G, further join this and it is perpendicular, the point is E. Let us see in triangle OAC, look at the triangle OAC, see, you can write in triangle OAC cos theta is equal to OA divided by OC, or OA is equal to OC cos theta, or OA is equal to X cos theta. OA is equal to X cos theta. In triangle, see the triangle CDP, this triangle CDP, sin theta is equal to CD divided by PC, or CD is equal to PC sin theta, or CD is equal to Y sin theta. But AB is equal to CD, see the figure, AB is equal to CD. Since ABCD is a rectangle, then the opposite sides of the rectangles are equal. That's why AB is equal to CD. In place of CD, I can write AB. So therefore the result should be OB is equal to, look at the figure, OB is equal to OA plus AB. OA plus AB, or I can write OB is nothing, OB is nothing, that is X dash, X dash is equal to, in place of OA, X cos theta, plus in place of AB, that is CD, that is Y sin theta. This is equation number 1. Similarly, where we can say OB is equal to, as we can say OB is equal to x dash along x dash axis. So similarly, in case of y dash axis, the mathematical construction looks like this. In triangle OEF, in triangle, see the figure, this point be F, OEF, the figure looks like this. In the triangle OEF, cos theta is equal to OE divided by OF, or OE is equal to OF cos theta, or OE is equal to Y cos theta. As OF is equal to Y, OF is equal to Y. Again, in triangle FPG, in triangle FPG, the small triangle FPG, sin theta is equal to FG divided by PF, or FG is equal to PF sin theta, or in place of FG I can write, that is EH. Let us write FG is equal to PF is equal to x into sin theta, but FG is equal to EH. See the figure, FG is equal to EH. Since EFGH is a rectangle, so the opposite sides of a rectangle is equal. That's why FG is equal to EH. Then OH is changed to that of OE minus EH. OH is the result of OE minus EH. OH is equal to OE minus EH. Or OH is equal to Y dash is equal to OE Y cos theta minus EH is equal to FC, that is X sin theta. For our convenient, we can write Y dash is equal to minus X cos theta plus Y sin theta. This will be equation number 2, as OH is equal to Y dash along Y dash axis. So we get X dash and Y dash. Finally, we can write z dash is equal to z as we rotate by taking z axis as constant. This one is equation number 3. See these three equations. Equation number 1, x dash is equal to x cos theta plus y sin theta, y dash is equal to minus x cos theta plus y sin theta, and z dash is equal to z. So, using equation 1, 2 and 3, I can write it in the matrix form as x dash, y dash and z dash is equal to cos theta, sin theta 0, minus sin theta, cos theta 0, 0, 0, 1 and x, y, z. These three equations are taken in the form of matrix. So, x, y, z, x dash, y dash, z dash, nothing but r dash vector is equal to this term, that is r of theta is equal to x, y, z is the r vector. This is the equation number 4, where we use r dash vector is equal to x dash, y dash, z dash, this matrix, and r is equal to, r vector is equal to x, y, z matrix, and also r of theta is the matrix representation of cos theta sin theta 0 minus sin theta cos theta 0 0 0 1, which changes the position of vector. So, in the entire discussion, r vector to r dash vector under rotation of coordinate axis about z axis in counterclockwise sense. So, r of theta is called the transformation matrix, is called the transformation matrix, or we can say that is rotation matrix. Also, we know that vector can be represented by coordinates of a point which are proportional to the vector components. So, the components of vector should transform under rotation of coordinate axis. So, let ax dash and ay dash be the components of primary coordinate system, and under rotation of that of unprimed coordinate system ax and ay axis. So, ax dash ay dash be the components of primed coordinates, and ax a dash be the components of unprimed coordinates. These primed coordinates are the results due to the rotation of that of unprimed coordinates by an angle theta with counterclockwise direction. So, we can write it in the components form See, Ax dash is equal to Ax cos theta plus Ay sin theta, and Ay dash is equal to minus Ax sin theta plus Ay cos theta. So, equation number 5 and equation number 6. Since the components of A along z axis remains unchanged, we can write Az dash is equal to Az. The equation number 7. In terms of x and y components, we find the magnitude of A vector. The magnitude of A vector as A x square plus A y square square root, the equation number 8. Also, under rotation of the coordinate system, the new components of the vector are Ax dash and Ay dash, so that the magnitude of new vector under rotation about z axis will be Ax dash plus Ay dash square root. We can easily solve out by putting Ax dash and Ay dash. So, the equation looks like this: Ax cos theta plus Ay sin theta square plus minus Ax sin theta plus Ay cos theta square root, that is changed to X square plus Ay square square root, which is same as that of equation number 8. In equation number 8, the magnitude of A is equal to the square root of x square plus Ay square. Similarly, that of magnitude is same, just like the square root of x square and Ay square. So, from the entire discussion, we can easily say, hence through the components of a vector may change under rotation by some angle, but the magnitude of the vector in the unprimed and primed coordinate system remains invariant. The magnitude remains invariant. This is an important property of vector. The vector is invariant, is the first property when the vector is rotated in a coordinate frame. As in the previous figure, the direction of that of given vector A vector remains unchanged or invariant under rotation of the coordinate axis through that of components of a vector may change in new values. Hence, the vector A vector is independent of that of rotation of coordinate system. The vector equations are independent of any particular coordinate system. So, we can say the vector under rotation is invariant. That means there will be no such change in its magnitude and as well as its direction. So, the overall topic, that is rotation of coordinate axis or the properties of vector under rotation, we can conclude that the vector is invariant under rotation. That means there will be no such change in its magnitude as well as direction. We can find out with the help of this mathematical method or by using this mathematical formulae. So, again we have to discuss how the scalar product of two vectors under rotation, or what is the property of that of scalar product under rotation. That is, since the result of the scalar product is a scalar, so it is invariant. So, we can say invariance of scalar product of two vector under rotation. How we prove this? Let us see. Scalars are independent of coordinate system, as we discussed. Scalar vector is independent of coordinate system, that is invariance under rotation, but we know scalars are also independent of coordinate system. Let us examine the behavior of scalar product of two vectors, one is A vector and another one is B vector, that is the scalar product. Under the rotation of coordinate system, what is that of result? If we consider the rotation of the Cartesian coordinate system about z axis, as we discussed in previous, by an angle theta, then as discussed the transformation of the components of A vector under rotation of x and y axis through an angle theta about z axis, we can write in the mathematical way x dash is equal to ax cos theta plus ay sin theta, and again ay dash is equal to minus ax sin theta plus ay cos theta, and az dash is equal to az, this is the constant along z axis. Similarly, for that of B vector, I can write bx dash is equal to bx cos theta plus by sin theta, and by dash is equal to minus bx sin theta plus by cos theta, and again bz dash is equal to bz. Hence, as ax, ay and az are the components of A vector along x, y, z axis, then A vector dot B vector is equal to ax bx plus ay by plus az bz. As obtained earlier, as we discussed in the rectangular components. So, if we dot product A vector and B vector with these results and find out A dot B is equal to this much, then we can say the scalar product of two vectors under rotation are invariant. So, let us find out the result. Ax dash, let us we observe what is the result, x dash bx dash plus ay dash by dash plus az dash bz dash. Put the values, ax cos theta plus ay sin theta into bx cos theta plus by sin theta plus minus ax sin theta plus ay cos theta minus bx sin theta plus by cos theta plus az bz. Now multiply these two, ax bx cos square theta plus ax by cos theta into sin theta plus ay bz sin theta into cos theta plus ay by sin square theta plus ax bx sin square theta minus ax by sin theta into cos theta minus ay bx cos theta into sin theta plus ay plus ay by cos square theta plus az bz. So solving this, I can write ax bx taking as common, that is cos square theta plus sin square theta plus ay by as common cos square theta plus sin square theta plus az bz. Since cos square theta sin square theta is equal to 1, that is unit, that is 1, so the equation changed to that of ax bx plus ay by plus az bz. See, as we discussed, a dot b is equal to ax bx ay by plus az bz. Similarly, for that of rotation, under rotation we can find ax bx ay bz plus az bz are same. So we can easily prove out the invariance of scalar product of two vectors under rotation. So with the help of this video lecture, we have studied that of rotation of coordinate axis, that is the properties of vector under rotation, and we can easily prove the properties how the invariance of that of vector occur, and again prove the invariance of that of scalar product of two vectors under rotation. So with this valuable notes, let me wind up this session. Thank you.